Gentlemen, welcome. Today in our online industry tutorial, we continue discussions on one of the most talked about materials in the tech industry today, thin-film lithium niobate. I'm John Pugh, Director of PIC and Quantum Technologies at Optica, and this is the first of 3 Optica online industry tutorials with Quantum Computing Inc., a company headquartered in the United States developing both hardware and software platforms that bridge the gap between classical and quantum computing. In today's tutorial, we'll hear about the incredible progress from QCI Foundry, which is enabling rapid prototyping and process-informed design for TFLN, a material platform for the next generation of computers, information processors, communication devices, and sensors. Remember, this is a very interactive event. We have nearly 500 people registered, so please ask your questions in the Q&A Zoom facility, and we'll address them at the end of the presentations. From tutorial sponsors, Dr. Puya Dianat, Chief Revenue Officer, QCI Foundry, and firstly, Dr. Milan Begliabekov, Chief Operating Officer of QCI Foundry. Milan, please share your slides. The floor and the attention of everyone is yours to tell us about the QCI Foundry story so far, and the incredible future ahead.
Thank you very much, John, and the Optica team for inviting us to speak and share some of our recent results about TFLN PICs. We at QCI are really excited about the future of this material and what this material can bring to the optics community. And as John mentioned, my name is Milan Begliabekov. I'm the Chief Operating Officer for QCI, and part of my responsibilities is bringing up and leading the manufacturing efforts for QCI. So here is the overview of today's talk. First, I'd like to introduce the company and who we are, and then I'll continue the introduction by giving everyone in the audience an overview of what is integrated photonics and what are the goals of the fields and the advantages that it can bring to revolutionize technology over the next few decades. And then we'll continue to explain what is thin-film lithium niobate and why at QCI we made the bold and decision to begin working with this material. And I'll conclude that part of the talk by showing you some of our recent device results. And those results will be focused mainly on 2 classes of devices that we have been making at QCI from TFLN. The first class are modulators, and then the second class are nonlinear optical devices that utilize periodically poled lithium niobate. And after that, we'll have a quick detour into quantum light sources, which we made leveraging our PPLN. And after that, Dr. Puya Dianat will introduce our foundry. And the goal of that is to show all of you how you can get involved and work with QCI and join us on this quite exciting journey of making TFLN integrated photonics a reality today. So who is QCI? QCI, the glue that holds the company together is nonlinear optics and nonlinear integrated photonics. At the moment, we have 2 primary sites. The first is the company headquarters in Hoboken, New Jersey, and that is where our hardware design, R&D, and testing teams work from. And a second site, which recently opened a few weeks ago, is our TFLN foundry that's located in Tempe, Arizona. And that is where we do PIC manufacturing, and we also have facilities available for prototype packaging and rapid assembly of our devices. The overall goal of the company is to make devices that leverage nonlinear optics. So for example, one of our machines, which we're currently working on and are quite proud of, is a quantum optimization machine. And this is not going to be part of the talk, but the reason I'm highlighting it here is because the overall vision of the company is to use nonlinear materials such as TFLN and take machines which are currently built out of bulky components and miniaturize everything and bring it down to chip level where it become adopted afterwards. So our company right now is rapidly growing. We're already up to 60 people, both in Hoboken and in Arizona. And we have expertise in not only optics, but all the other necessary skills needed to take something out of the lab and bring it into production, such as hardware engineering, fabrication, embedded design, algorithm development, and firmware development. So we really are a full stack company that is now growing. And if you're interested in getting involved with us, please reach out. We are going to be onboarding new people in the very near future. So why are we interested in this field of integrated photonics, and what is it that we're doing that's exciting and new? And one way to understand this is to look at what happened in the past 50 years with Moore's law. This, I think, is a chart that's quite familiar to most people in this audience. And what we see here are really two things: the increase in the number of electronic devices on a single chip has not slowed down until very recently, but also the decrease in price that accompanied that. So this is what I'm showing here is an Amazon link I pulled down last night. So for approximately $250, you can buy the latest generation of an Intel processor that has tens of billions of transistors and active electronic elements. So the field of integrated photonics, what it is trying to do is leverage the same semiconductor manufacturing technology that ushered in the revolution for electronics, but do so for photonics. So we're using essentially, if you go into our labs and especially our foundry, what you see are exactly the same types of tools and the same types of processes that are used to make silicon electronics. We're just using them for a different purpose. And in particular, in our foundry, we're using them for a slightly different material that's not silicon, and that is thin-film lithium niobate. Why are we doing that? Using light, it allows you to take advantage of additional properties for modulation, for encoding, for data transmission. So instead of just having electrons that flow down copper wires, we have light in waveguides, and that allows us several additional degrees of freedom, such as we can play with the intensity of light, and that's the only analogy that we have with the electronics world, the on-off transistor type devices. But now we're able to store information in the wavelength of light, in its color, in polarization, and that is the orientation of the electric field in the fiber. And we're also able to leverage quantum properties such as entanglement to really bring in a new paradigm of technology. And if we're able to harness some or all of these properties, we can really usher a revolution in things like computing. Both classical and quantum computing can benefit from this technology, but also artificial intelligence, remote sensing, lidar devices, biological devices now have an entirely new playground that could be used to make chips that'll revolutionize these fields in the next decades. So making things smaller has several advantages. There is the obvious advantage of taking an experiment which in the past filled rooms with optical benches and condensing that onto a single chip. So the picture that I'm showing here is an experiment from the Hansen lab in TU Delft. It's a teleportation experiment. And now we're able to take those components, most of these components, and miniaturize them and put them on chips. And doing that, in addition to making things smaller, brings you other advantages. And the other major advantage is stability. If you look at the size of this optical table, a mirror that's closest to you, it's going to experience slightly different temperature, for example, and vibration that the mirror on the opposite end of the table. And there's quite a lot of work involved in maintaining this infrastructure. If you shrink everything down to a size of a small chip, then all these complications suddenly vanish. So that's yet another, and in my opinion, much more powerful motivation for pursuing integrated photonics as a field. So if we want to do this, the next question that we would naturally ask is, what types of devices do we really want to put on this chip? And they really belong in four classes or categories of devices. First are the light sources. You have to generate the light, and that's typically done by a laser or some sort of a light-emitting diode. Then there are the passive devices, so you have to move the light around, and you can think of a mirror or an optical fiber. So that's an analogy for a wire. But ultimately, what you want to do is you want to do something to the light that's on the chip, and that's where the most interesting devices come in. These are active devices. They do something to change the state of the light. And there's several flavors on those. They're the electro-optic devices, and that I'll mention in the next few slides. And they're also nonlinear devices, and those are things like frequency converters that either change the color of the light or filter out a certain portion of the spectrum. And after you do this, you have to detect the light. So they're the conventional photodiodes that most people here are used to seeing, but they're also superconducting photodiodes, and those are quite useful when you're working with single photon light sources, such as required for some quantum applications. So the primary focus of the QCI foundry and the primary advantage of TFLN, thin-film lithium niobate, as a material is really for actives, and you'll see why in a second, but also it has some advantages for passive devices. It's a very transparent material, so you can move light around on a chip with very few losses. Of course, if we want to have a complete ecosystem of components on chip, we have to ultimately integrate light sources and detectors, and our current plans for doing that are for using co-packaging and heterogeneous integration. So why did we choose thin-film lithium niobate of all the materials that are available to us to work with? It's certainly not a standard material like silicon, for which there are decades of process technology and process knowledge that's available. So if we are moving away from that knowledge, there has to be a good reason to do so. And we believe there is one. So from a very high-level theoretical perspective, let us ask the question, if we were to choose an ideal material to work with, what are the properties of that material have to be? And one of the requirements, and it's very nice to have, is a material that has a very wide transparency window. So, for example, all long-distance telecom communication is done at around in the C-band around 1550, the O-band around 1300 nanometers. That's very commonly used for short distance communication, but also for high speed, high capacity inter-data center type of communications. And if you want to do remote sensing or biological sensing and imaging, well, that's typically in the visible range. So if you have a material that can cover that transparency window, then that's a very good candidate for integrated photonics. If you want to make devices, and in particular, I'm talking about active devices in this particular case, then you want a material that has large electro-optic coefficients for both polling and for modulation, and I'll explain why those are necessary in the remainder of this talk. And then the final set of requirements comes from manufacturing. We are as a team, with a team that came out of academic labs, and in academia, it's great to make materials that make and devices that make all kinds of superlative claims. I made the world's best transistor, or I made the world's device with the highest on-off ratio for electro-optic modulator, for example. But ultimately, what you want to do is you have to manufacture that device, and the number of dies we're talking about are millions and tens of millions. So we need something that's thermally and mechanically stable. It has to be compatible with CMOS, because CMOS is not going to go away, and it has to be compatible with existing foundry flows. So if we look at the periodic table and basically ask the question, well, what materials can be used to do this? These tend to be non-center symmetric crystals, something like transition metal perovskites have all the required properties that I mentioned. And these are materials like barium titanate, lithium titanate, and lithium niobate. So at QCI, what we did is we made a decision to focus on lithium niobate. And the reason for that decision, that's the supply of lithium niobate wafers right now is the most mature in all of industry. But we're also actively looking at lithium tantalate as a material that we can work with. And in the future, we're having discussions whether or not we'll be able to accommodate barium titanate, which is another emerging material for these types of devices. And TFLN has not only the most mature and robust supply chain today for these types of materials, but also in the past decade, there have been numerous demonstrations from various groups of TFLN devices that are useful for high-speed switching above 110 gigahertz with wide bandwidth and low VPI. It's a CMOS compatible material, and it has very low operational losses, less than 10 dB per, less than 0.1 dB per centimeter. And that really enables you to make devices for datacom markets for high-speed modulation and high-density data encoding. And these devices leverage various types of electro-optic effects and nonlinearities that are present in PPLN. And I'd like to share some of those with you now. So the most widely studied and the most interesting device from a point of view of industry adoption are lithium niobate modulators. Lithium niobate modulators in themselves are not new. They're probably a 60-year-old technology. So what I'm showing at the top is a modulator that's available commercially today that you can buy off the shelf from any supplier of optics. And what's inside this device is a Mach-Zehnder interferometer. So the light comes in on the left, and you can apply a bias to one of the gold pads that you see in the image. That bias is going to create a phase shift in the upper or lower arm of the interferometer. And when you combine the lower and the upper arms, the fact that you introduce the phase shift is either going to extinguish or amplify the light. So you can think of this as a type of device that converts electrical signals into optical signals, and it's very widely used in industry for this purpose. The bottom portion of this figure shows how this is done conventionally. What typically people do is they take bulk thin lithium niobate, they indiffuse some titanium into it, and the titanium in diffusion creates a waveguide, and that waveguide is what gives you the index contrast in order to route the light in the material. And that has a major limitation. The optical mode is going to leak out into the bulk device, and that's going to limit the speed with which you can work. So the advantage that thin film brings you is the ability to confine the optical mode into very small volumes. So what you see on the right are some EOMs that were made at QCI, and that chip is several millimeters, not centimeters long. So not only are you able to do this in a very small form factor, but you're also now able to achieve much higher modulation speed because you're achieving much better mode confinement in the waveguide. So here are some electro-optic modulators that we worked on in the past at QCI. The image at the top is actually showing a cascaded device. So these are two EOMs that are cascaded together. And for some applications, in particular quantum applications, it is advantageous to have a high extinction ratio. So that's the difference between the light on and light off signal. And what we're showing that with a single device, we're able to achieve approximately 25 dB of extinction. And if you cascade these modulators, we've been able to achieve up to 55 dBs of extinction in an on-chip device. Here's another flavor of modulator that we worked on at the company. The idea there is for certain applications, what you care about is the V-pi length product. So that is how much voltage do you want to apply to a device before you extinguish all the lights. And what we have shown is that by extending the electrodes over the top of the lithium niobate waveguide, you're able to achieve quite low V-pi length product down to 0.7 or 0.6 volts. The predominant interest in electro-optic modulators is for high-speed switching, for pluggables, for datacom and for telecom. And TFLN offers the ability to realize very high modulation speeds at very energy very energy efficient in a very energy efficient device. So we very recently began designing and fabricating RF modulators for high-speed datacom and telecom applications. And our initial devices are showing pretty favorable for a 44 gigahertz bandwidth at measured up to 60 gigahertz. And these are not the latest results. And our latest results are actually showing even higher modulation bandwidth and also higher switching speeds. And we plan to extend this device beyond 110 gigahertz in the very near future. So the second area of interest for making TFLN devices is to use TFLN for nonlinear optics. And the types of devices that are really interesting for this purpose are the so-called PPLN, periodically poled lithium niobate. So periodic polling, again, is not a new technique. That's something that has been around for decades. And the idea here is if you have a material such that is ferroelectric, such as lithium niobate, if you invert the ferroelectric domains, either in a waveguide or in a microring, and you do so with a certain periodicity, that's going to allow you to match the momenta of light that is propagating in this crystal. And doing so, you're going to be able to realize very efficient frequency conversion, as well as other nonlinear optical devices. So I'd like to share with you some of the devices that we made before. So here is a periodically poled lithium niobate waveguide. In order to achieve the periodic polling, what we do is we deposit an array of electrodes on top of the device and apply a large electric field between the electrodes that inverts the ferroelectric domains. And when you turn off the electric field, the domains are just stuck there. So you have a periodically poled waveguide in this particular case. And in the application that I'm showing in this slide is you have a highly tunable second harmonic generation waveguide where you're able to, by changing the temperature of the waveguide, you're able to tune the wavelength of and the conversion efficiency in a certain wavelength range. You can do the same thing perhaps more easily if you realize a microring. So the device that we're showing here is a ring that has been periodically poled, and we patterned a heater on top of this ring. This is what you're seeing at the bottom left of your screen. And by applying a fairly small current, what we're able to do is we're able to change the transmission of this ring that was shown in the middle of the screen. And we're doing so with pretty favorable efficiency numbers. So here is perhaps the last PPLN device that I'm going to show you. So this is a micro ring resonator where we're polling a portion of the ring. And the idea here is to increase the photon-photon interaction. One way to measure that is to measure the total photon lifetime, which corresponds to the total cavity length. And what we determine in this measurement is that this particular cavity, which you can see on the screen, it's about that it fits in a sub-millimeter chip, but it has a total interaction region for light of 2.7 meters. So that really shows you why this is a very powerful technology for bringing nonlinear optics onto a chip. We have done a little bit of work, although this is not our primary focus of the company or of the group, on generating frequency combs. So these are devices that you pump with light, and the output is a bunch of isolated almost laser lines at different frequencies. And you can think of this device as something that's useful for spectroscopy, for chemical sensing, because you have something that's almost like a broadband light source. And this work is something that's currently ongoing at QCI. Here's another device that we've built for our partners at NASA. So this is a microring filter. So the idea is you send light and into the device, and what comes out is only light that's on resonance with the cavity. And what we're showing at the bottom left is how we're able to shift the resonance of the cavity to different wavelengths by just applying a voltage to the filter. And the reason this is exciting is because the image on the bottom right of the screen is a carbon dioxide spectrum, which we're able to collect using this device of the spectrometer. So the chip itself is in the middle of a screen, so it's a approximately centimeter-sized chip that we're able to use for spectroscopy applications that are very interesting to our collaborators at NASA. And this work is still ongoing. Here are some more recent devices, and you see that we've been able to repeat this now in the visible range. So the center, the cavity wavelength for this particular ring is at around 770, and we're able to tune that wavelength quite linearly. That's what we're showing in the upper right portion of the screen. So before I leave you, I'd like to tell you about one last project which we're pursuing at QCI, and that has to do with the namesake of our company. We're interested in quantum devices, and in particular, we're interested in making quantum light sources. So what we want to do is generate entangled pairs for quantum networking and quantum communications. This is quite easy to do with periodically pulled lithium niobate. So the device at the bottom right of the screen is a box that we made that uses, for the moment, bulk lithium niobate that has been periodically pulled. And this is something that we have commercially available at QCI. So you pump that with some frequency of light, and then you get simultaneously high order numbers of photon pairs. So today we're getting 48 photon pairs simultaneously at 1550, but also at other wavelengths. And we've done some work quite extensive work to characterize this device, and it seems to be quite stable, high bandwidth, high brightness quantum light source. And of course, the reason I'm telling you this is here's a preview of some of the recent results. We're trying to achieve the same thing, but bring the technology on chip. And that work is currently ongoing, but we're quite encouraged by the results that we're seeing. So with that, I'd like to introduce my colleague, Dr. Puya Dianat, who will speak about the QCI Foundry and really the next steps for this part of the business.
Well, thank you, Milan. And hello, everyone. I'm Puya Dianat. I'm the Chief Revenue Officer here at QCI. And actually, I'm going to spend a few minutes with you to talk about our foundry, or QCI Foundry, the services that is available, and basically how you can get involved. But to get to the foundry, let me give you a little bit of background of how the Quantum Computing Inc. decided to basically build the foundry. So many of the technologies, the core technologies that we have within the company are related to photonics and quantum technologies. And what we focus on is basically capture data or do sensing and measurement. We do computing operations on them, and we then communicate them. So these three aspects all have in common the photonics and the quantum part. And the key enabler of all of these technologies that we have and all of the products that we have is lithium niobate. And it is our goal to take these boxes that we have right now and miniaturize them in the long run. And the key enabler of that is thin-film lithium niobate technology. So when during the course of the development of the company, when Milan and the team and everyone were working on these devices, the initial devices were being supplied through work in university user facilities. But the quantum applications are so demanding that we need basically a dedicated resource to ensure that we can get high quality devices made exclusively for these applications to, for instance, increase the quality factor or reduce the propagation losses in waveguides and these metrics that are common for nonlinear optical devices. So the company strategically decided to build the fab, and the foundry is a byproduct of that. It's been in the making for the past couple of years. Here are some of the tools that we have put in the foundry. Exclusive to us is basically many of these tools are custom made for thin-film lithium niobate. So everything is built from scratch and based on the knowledge that the team had gained through many years of how to process thin-film lithium niobate and particularly how to etch thin-film lithium niobate really well. These equipments were obtained with leveraging those knowledge and were custom made. And the facility was built in Tempe, Arizona. And as of May 12, we had our grand opening or ribbon cutting ceremony that happened, as you can see in the image in here, showing the team celebrating this occasion. But this foundry that we have is a US-based foundry for thin-film lithium niobate. It's tooled to process 6-inch wafers with cassette loading capability. We can do prototyping to medium volume manufacturing. Currently, we at this stage, at this phase of the foundry that we can process up to 1,000 wafers per year. That capacity can increase with time, with operational efficiencies that we will be going through. And we expect to have chip delivers later this year. And we will have MPW offerings in the third quarter of 2025. Our in-house process includes the lithography, and we use a high-speed e-beam writer, and that's actually the key tool that we have that enables us to do very fast prototyping of the designs of the circuits that we receive. We have the expertise of etching the lithium niobate and thin-film lithium niobate, and we can do oxides, nitrides, and silicon etch as well. And we can do metal deposition, and we can do back-end processing of dicing and prototype packaging in a limited quantity format. We also have the team that is the experts in these fields and in PIC design and in characterization. And we have in-house capabilities to assist you with FTTD simulations, impedance matching, impedance analysis, and characterization as well. And we are looking into making the 100 gigahertz RF characterization testing and measurement capability added to our facility later this year. We expect that to be in Q4 of this year. Now, the key thing, as I mentioned a couple of times, is with this technology, we can etch thin-film lithium niobate really well to reach sidewall roughnesses that are as small as 300 picometer or less. As you can see in the AFM image, in the middle and the bottom right, the data that we have, the surface roughness is very small. This is very smooth. It is important to reach these targets because quantum applications require very low loss waveguides and very low scattering from the sidewalls of the PPLN structures, for instance, in the microring PPLN that you see in here. And in order to minimize those scattering on the sidewalls, the etching is a critical part, and that's one of our capabilities, major capabilities on the in this foundry that it's available. Its services are available. We have also demonstrated previously the capability to put multiple components, optical components, on a photonic integrated circuit. For instance, what you see in here is on the top left is a PIC circuit with a phase modulator, PPLN micro ring, and inverse taper. And you can see some images of it on the bottom left as well. We can put many different components on the circuit, Bragg mirrors, MMIs and such, inverse tapers. And we can also work with variety of different kind of wafers, doped thin-film lithium niobate, X-cut, Z-cut, or Y-cut. Although our standard PDK are only focused on one aspect of these, and that's on X-cut mainly right now. We have the capability of how to control the sidewall angle of the edge, and that gives us the capability to have V grooves and U grooves on the chip. And by controlling the sidewall angle, we can control the fiber placement on the chip, and that way we can control the losses, the coupling losses. And we have demonstrated that we can get coupling losses as low as around 1.5 dB per facet. And like I said, that comes from the capability that we can accurately control for a V groove, we can accurately control the angles of the sidewalls. We will have, like I said earlier, we will have the MPW offering later this year in Q3. But the main difference between the QCI foundry and other foundries that you may know is that we leverage the high-speed e-beam rider technology that we have. So we are using the MPW term as a term of business, but we are doing it a little bit differently. So ours is basically an MPW 2.0. With that, you will have a flexible schedule. We don't want you to rush into submitting the designs that are not you don't feel necessarily comfortable with, to just meet a tape out date. And basically, we will have a flexible timeline for you to submit your designs and work with us. And we will have a very fast turnaround time so that you get to see your results very fast, so that you can either iterate, publish your data, or for graduate students, get your degree faster. And basically, we are trying to decrease the pain that we think with the conventional or traditional MPW run exists. We don't have those bottlenecks, and we are basically offering those flexibilities to our customers base as well. Additionally, through our MPW runs, we will offer an interface to our customers through GDS Factory Plus, and that comes standard with our future MPW runs. That you will have access to GDS Factory Plus for a limited time, for the time that you need to do the design, and to be able to have a usable interface and not get stuck into the Python scripts only. You will have a very good user interface and be able to leverage that. Our standard PDK right now is designed for 1550 nanometers, and it's based on a 600 nanometer thin-film lithium niobate on a buffer oxide. And if you want to get more information on the foundry or on how to work with us on the MPW run, you can reach out to us at the email that you can see on the screen. Our current PDK is the demo PDK is available on GDS Factory. We ask for whoever wants to work with us to sign an NDA, and we can then at that point provide the access to GDS Factory. We plan on unveiling our PDK on other platforms as well. Lucida mainly is going to come out, and we will have it for different wavelength as well for O-band later on. And we also are working with some of the partners that we have that are helping us in coming up with the design and enhancing our capabilities. Namely, Spark Photonics have been a very good partner with us, as well as Alcyon Photonics, which is a design house for photonic integrated circuits. And we hope that and those are also other avenues that you can reach out to us. To show you the demo PDK and the interface and the capabilities that it has, you can see that with the GDS Factory Plus, you can really visualize and do these circuit routing really easily, and you can see all the elements on the that exist in our PDK. I think it's close to 30 elements that we currently have. You can see it on the left side of the screen, and it makes it for a very user-friendly interaction with to the photonic integrated circuit. Again, our approach to MPW is to minimize the pain that the designers would go through, and we want you to just focus on the design and not having to deal with learning 15 different fields just to be able to use to design the photonic integrated circuit. And you can see some of the data that is available on the PDK. For instance, here we have the MMI, so different specifications that and visualizations that are available through the PDK. And additionally, here, for instance, you can see an EOM that is available on PDK on GDS Factory with some simulation results and some characteristics, as you can see done in here. And with that just brings me to my final conclusion that the QCI Foundry is now open and available to offer you services for your custom runs, as well as if you want to leverage our standard PDK and do the design all on your own, we'd be happy to provide that as well. And we'll be happy to provide you with custom runs in which we will be more involved in helping you with the design, or provide you with variation in the wafer thickness or waveguide, or even assist you in different stages of your design. So this is a fairly comprehensive PDK that we have available, and for thin-film lithium niobate, and I'm hoping that we've demonstrated the capabilities that we have to you in this webinar. So with that, I would like to thank you everyone for attending this, and we are happy to take any questions, Milan and I. Thank you.
Great, thank you so much, Milan and Puya. Many comments are saying what a great talk. Congratulations on all the progress you've made so far. We've now got time to address the questions, and there's some come through in the chat and Q&A. So going back to the modulators, Milan, you mentioned about the cascaded modulators. I think that you mentioned numbers of 20, 25 dB for single modulators. Is there a path or a goal to reach maybe 30 dB extinction ratio there?
Yes, that's certainly what we're working on. If you're talking about a single modulator, in particular, 30 is doable, but it relies on the question then becomes, how good is your fabrication? So if there's a little bit of an inconsistency in the beam splitter that can be introduced during etching, that's where you will see degradation in the extinction ratio. So 23, 25 is what we typically see, and as we improve the process over the next few months, our goal is to get to closer to 30, but beyond that, we see that you would have to cascade the modulators to achieve that type of performance.
Okay, great, thanks. So for the use case of the high-speed switches, there's a question from Camille Optica from Ligentech asking about the, what is QCI's way of dealing with the bias drift during the static hold time of a switch? Could you comment on that?
There's not too much I can say about that. We are working with several partners on high-speed switching, so a lot of that work is proprietary, but the standard techniques that you would think of with off-chip locking is something that we're actively looking into.
Great. And another fairly technical question on the modulators. The power versus phase shift graph is not sinusoidal. What's the origin of the non-sinusoidal deviation? Can you comment on that?
I cannot offhand, but I can certainly send you the publication where we discuss more details, and I think those details are available in that paper.
Fantastic. And later on in your talk, you discussed the tunable filters. Is there any sort of what's the sort of theoretical limit with TFLN of how narrow the tunable filter can be, even if it's fixed?
Yes, we can talk about the quality factor more so.
Yeah, maybe
Yeah, so I think theoretical limit for the quality factor that we can get that determines the resonance and the width would be around quality factor of 100 million, if I'm not mistaken. And that is where you can get. Now you can translate that into how narrow that becomes. But right now, I think the devices that we have shown has the quality factor of a little bit less than 5 million. So you can imagine do some rough order calculations of the theoretical limit, what you can achieve, and what currently state of the art is. So our goal is to increase our quality factors to 10 million and beyond that.
Great, thanks, Pia. So there's a few comments and questions in the chat about you mentioned earlier the supply of lithium niobate wafers is fairly plentiful, and that's why you work with this material at the moment. So when you get the wafers in, can you tell us about how you might characterize the substrate and possibly the modulators once they're made? You know, what techniques do you use and what are the challenges?
Sure. We can comment a little bit on that. So, to add to the question, there are the few well-known suppliers that a lot of groups currently leverage to get their TFLN. We are currently validating several suppliers in Japan and Europe, and also some in the US, to create a more robust supply chain that is very resilient. And we're seeing more and more offerings that are getting better and better every day, and not only with the TFLN, but also with thin-film lithium tantalate. As far as the validation steps, we do the standard kind of ellipsometry and white light interferometry to characterize the uniformity and TTV of the wafers. And especially when it comes to PPLN, the height variation of the waveguide is very important. So at the moment, we're developing techniques to scan the PPLN, the waveguides, to understand what the TTV looks like and use that to inform our designs. And also we're developing technology for in situ monitoring of polling to improve the yield of that fabrication process.
Great. And when you're polling on sort of a chip scale, you mentioned about the bulk scale device. Is it very repeatable, or is something like lithium diffusion a problem? Do
So
you see?
at the moment, I think you precisely identified the issue. The yields of PPLN devices are very low. And there are several things that contribute to that low yield. One is the lack of in situ monitoring of the polling process. That's something that we're actively working on. The other one is just the height variation of the waveguide can significantly affect phase matching. That's another project that we have to tackle. So at the moment, it's not yet a wafer scale technology, but that's something that we're working on quite actively in the next in the near future to overcome.
Great. And there's a fairly technical question on polling in the future. Do you plan on providing apodized polling in the future? Would that be very difficult?
That's not something that we looked in currently, so we don't know at the moment.
Great. And you showed PPLN for Z-cut lithium niobate. Do you also have the process established for X-cut lithium
Yeah,
niobate?
we've tried both X and Z cut, and for some technical reasons and yield issues, we're at the moment focusing on Z-Cut. But we have done X-Cut as well.
Great. So going into this sort of MPW, you mentioned, Puya, about not giving people too much of a deadline. I've been there myself in trying to meet a deadline on an MPW. So that's fairly flexible. What are the turnaround times on the MPW planned?
Sure. So we expect to within 90 days we deliver to customers after they submit their designs. In practice, that may be much faster. The 90 days is what we feel comfortable communicating right now, but we think that in reality we can cut that down to two-thirds of the time that I said, but 90 days is our standard time.
Great. And there's a question about sort of firewalling IP from a customer. So the customer designs for the MPW, or even if they go for the whole wafer, do you sort of firewall that from your internal product development work?
The answer to that is yes. We are offering this service to the industry because we think that there is a lack of such service available to people, and we don't intend to compete with our customers. So we have processes in place to ensure that the customers can share their IP with us for their MPW runs, and make sure that is not going to find its way into our product. So we don't plan on competing with our customers and be a pure play in that sense. Of course, that said, in the quantum world, it's a very small world, and everyone is talking to each other. And for different quantum customers, we are having conversations with them as well, and the things that we can do with them.
Great. And you're currently using 6-inch wafers. Is there a plan to increase to 8-inch, or is that not in the sort of roadmap?
The 8-inch wafer, we theoretically in our current plan, with some modifications, we can accommodate that. But the reason that we have decided to stick with 6-inch is that that's where the quality of the wafer is the highest right now. For 8-inch lines, the yield hit that you may get doesn't justify the increase in volume that you can get from the chip. So we think in terms of serving the volume the volume orders that will be coming through in the next few years, 6-inch would still be the critical part because it provides the best yield out of the process. Great.
And in terms of the MPW, are you able to comment a bit more on the range of different things like are you able to offer a Bragg filter, for example, or is it just standard components you can offer?
So our standard components are available on our standard PDK is available on GDS Factory. It's all around 30 elements. I mean, if anyone is interested, we can, like I said, execute an NDA and provide access to that for people to go see what is in there. I cannot make comments beyond that publicly here.
Very understandable. And you're able to say how many technology steps are in that MPW, or is that contained within the same?
I think that's part of the that would require an NDA before we can disclose.
Sure, great. So you mentioned that you weren't kind of averse to moving to different materials in future. BTO was mentioned at the start. Can you comment on so there's a question about lithium tantalate capabilities. Do you have any at the moment, or is that you just solely working on TFLN?
I can comment on that. So I think the good news is that the process technology and the processes required to work with lithium tantalate are nearly identical to thin-film lithium niobate. So that is something that we can easily do. At the moment, we purchased several lithium tantalate wafers and kind of are evaluating them. We haven't seen too much demand from our conversations with our customers for lithium tantalate, but if the demand picks up, we can very easily accommodate it.
Great. There's a couple more interesting questions coming. So you mentioned about your expertise on nitrides. Can you comment on the possible integration of silicon nitride or silicon oxynitrides with TFLN?
Yeah, so I think that's a very interesting direction, which we haven't yet pursued, but we definitely intend to pursue. And I think the easiest way to do that is to grow PECVD nitride on top of a TFLN, and that gives you a very good path towards hybrid integration. And we are in discussions with some partners as to how to do that. But we don't have any results that we can share at the moment.
Sure, great. The follow-up question from that was, do you have a roadmap for laser and photodiode integration? So that kind of goes on the same vein there.
Yeah, and I think roadmap, it's too premature to call it roadmap at the moment, but we're actively evaluating the possibility of that integration, yes.
And you mentioned that you use your fast e-beam for the writing. What is the resolution you offer with this e-beam? And also, do you offer any DPV lithography?
We're working with partners for DPV lithography. We don't own a stepper ourselves. The resolution, you can easily go down to 50 nanometer resolution with this tool without any tricks. And with tricks, you can probably push it to 25, but that's not something that's necessary for this type of work.
Great. And if somebody uses the MPW to evaluate the process and they want to move to volume production, is there a strategy on how customers could scale up the production beyond MPW?
Yes, they are part of our long-term strategy. Some portion of it I cannot disclose publicly, but that is something that customers can work with us confidently, that they can work with us on the MPW run, and we will have a path for volume production for them. But we can discuss those on one-on-one conversations. We cannot disclose it publicly at this point.
Great. And so it seems with Fab 1 that you've just built and opened a couple of weeks ago in Tempe, Arizona, it seems like you built and qualified this fab in record time, which is real testament to the experience of the team, I guess. So can you comment on some of the biggest technical or strategic challenges you faced during that process and how you overcame them?
Well, there are a lot. I think we really leveraged the experience of the team, and this is not the first fab that I personally built, and several of our team members have had over 30 years of experience doing that. But the biggest issue right now that we see is just the lead times with equipment, because there's so much demand. But so the equipment that we have installed in our fab, some of it had 1.5 year lead time, so we had to order it in advance and do a lot of the planning before it arrived on site. But other than that, we were lucky in the state of Arizona has very favorable policies towards building this type of infrastructure, so we didn't face any major challenges in doing the building process.
Great. And a final question maybe on the sort of the world of chip testing. What bottlenecks have you encountered in photonic testing or chip testing, and what difficulties would you like to be resolved right now?
So I can take on that one. As the frequency of the EOMs bandwidth is going higher, the expertise on delivering on those becomes more and more scarce. So that capability we need to be more widespread available. Also, with that comes the having the right packaging is structure available. That is another challenge that may also find its way into testing. So I think in my slides I showed that we have plans of bringing some testing in-house just because of that lack of immediate availability and fast turnaround that we are offering to our customers. We would like on the testing side, we receive similar things from the market, and we currently have a little bit of lead time in the testing. So those are the challenges that are available. The lack of availability for high bandwidth testing and measurements, and that is a challenge.
Great. So we start on time and we finish on time at Optica. So please get in touch with the team at QCI Foundry, particularly if you're looking to partner and use their Foundry services. Once again, I thank Milan and Puya and all of QCI Foundry for sponsoring this industry tutorial brought to you by the great team at Optica. So we'll get together with QCI again on September 18th, same time, same platform. So look out for that. So thank you all so much for attending. For your attention and questions. Bye for now.
Thank you all.